Okay, so I was just practicing of how I would study, and first thing I would do is try to solve the problem, and I wrote out a solution, and I think it's pretty good. So then, to make sure I know it, I would just try to solve it again. So but this time without looking, and then I'll compare to how I did before. So let's see. Let the G's be a Grobner basis for some ideal. Describe how these Grobner basis elements can be used to solve the ideal membership problem. Okay, so basically, I remember that the answer is to test if F is in I, that's the ideal membership problem, it is enough to use the division algorithm and then I'll put the formula that this produces is F equals some quotient times G1 plus etc. all the way to some quotient times GS. So I'm dividing by the G's. And then plus R, where R is a remainder. And so I'll just sort of finish my sentence from before. It is enough to use the division algorithm and see if R equals 0 or not. So R equals 0 implies that F is in the ideal, and then R is non-zero implies F is not in the ideal. And so that solves the ideal membership problem. Now, I should say, why is this true? So, recall that R is called, is the remainder. And then I have to know what this word means. This word has a very specific meaning, and so I have to remember it right now. R is called the remainder if none of its terms, so R is a polynomial, so a polynomial is a sum of terms. If none of its terms are divisible by any of the leading terms of the G's. So this is the definition of a remainder, and this is the division algorithm. It produces this R, and it produces it so that none of these leading terms will divide any term here. If one of them did divide a term here, then we're not done. We're not done with the division algorithm. Okay, so this is what remainder means. And then I have to remember, what does a Grobner basis mean? But a Grobner basis means that the LT of GI divide LT of F for any F in the ideal. So, basically this is the property that the leading term, the monomial ideal generated by all the leading terms of every possible polynomial in the ideal is equal to the monomial ideal generated by these finitely many monomials. And, basically you can prove that this is equivalent to this. Okay, so now I'm getting a little lost, so I have to think about what am I doing. So to test if F is in I, we use the division algorithm and see if R is 0 or not. And this is the answer. If R is 0, we've solved it. It's in the ideal. If R is non-zero, then it's not in the ideal. Now, why is this true? Well, R is produced so that none of its terms are divisible by the LTGI. But a Grobner basis means that the LTGI will divide anything in R. Okay, so now I have to think, how does this all tie together? So I guess I could try to prove this part. So let's prove that. So maybe I'll choose another color. R equals 0 implies F in I. Can I prove this? Well, so if r is 0, then the division algorithm says that f is q1g1 plus qsgs. Okay, so by definition of ideal, f is in I, right? It's a linear combination of generators of I. A Grosvenor basis also has to generate the ideal. Okay. Perhaps I should even put that. A Grosvenor basis generates I and also has this property of monomials. Okay, so that part is proved. Now, what about this part? So, to prove this, let's prove it by the contrapositive. We'll say that f is in the ideal, and then we'll show that r must be 0. So if p implies q, then we can also alternatively prove that not q implies not p. Okay, so let's assume that f is in the ideal and try to prove that r is 0. Okay, so if f is in the ideal, then what will happen? So let's see. I need to show that r. Okay, so let's assume that f is in the ideal, right? Say f is in the ideal. Now say that r was non-zero, and we'll show that it really has to be 0. So, or I don't know. I mean, I'm just going to do some calculation. So if f is in the ideal, then f minus the q1g1 minus the qsgs, well, that is in the ideal. Okay, but this is r. So I just took these and moved them to the left-hand side by subtracting them, and I show that, so the r is in the ideal. Okay, but then, but the LTGI must divide its leading term, then. Its leading term. In other words, LT of R. But this contradicts the division algorithm. So R has no terms. Well, okay, that means R is 0. Done. Okay. So that looks pretty good. I think that's good. So I've showed why this is true. All right, this is the solution up here of the division algorithm. We divide, and if r is 0, it means one thing, and if r is non-zero, it means the other. And that solves the problem. Now we look back over here, and my solution over here is very different. I guess I rearranged the order, and that's okay. But you'll see it does the exact same thing. So, pause the video and you can read this solution. Both of these solutions are correct, and your own variation of these solutions will also be correct. But the key here is that I just repeatedly see, can I explain this again without looking? And if I get stuck, then I should go back to the book and figure out, was it that I didn't know what a remainder was? Maybe that was it. Maybe I didn't know the property of a Grosvenor basis. Or maybe I just didn't see that I could do this little subtraction. So there's many things that could go wrong or that I could forget. And you just go back to the book and find out which one. Or I guess you can go back to this video too.